In this lecture, we look at planetary orbits, or the orbits of planets around our Sun. Closed orbits are ellipses. For example, we have the Sun at one of the foci of a planetary orbit, and our planet moves around this ellipse on the dotted curve. We note that it moves faster near the Sun, and that the line joining the Sun to the planet sweeps out an equal area in equal time. The circular orbit is a limiting case of an ellipse, and on that orbit, the planet travels at a constant velocity around the orbit. These ideas are a summary of Kepler's laws, or many of Kepler's laws. There's an additional Kepler law known as the Kepler's Law of Periods. That says that the period of the orbit squared is equal to the quantity 4 pi squared divided by the universal gravitational constant g, divided by the mass of the central object, in this case the Sun, times a cubed. A is the length of the semi-major axis of the ellipse. As shown here, if the orbit were circular, a would be the radius. One of the powerful things about this is that it depends only on the mass of the central object, this capital M. If we measure the period and we measure the semi-major axis, then we can find the mass of the central object. So let's look at an example where we determine the mass of a black hole. A small star is observed in a circular orbit around a dark object. The radius of the orbit is 3 times 10 to the 13th meters, and the period of the orbit is 10 years. So what is the mass of the dark object? Well, using Kepler's law of periods, we write that down, and then we solve for the mass of the central object, and then we go ahead and plug in our numbers. So we have 4 pi squared divided by capital G divided by the period squared. Well, the period in seconds is given by taking the number of days in a year times 10, so we have 3,650 days in 10 years, times 24 days, times 3,600 seconds per hour, and that gives us the period in seconds. And then we have to multiply this whole thing by the radius cubed, so that's 3 times 10 to the 13th meters cubed. Putting this into our calculator, we find that the mass is 1.6 times 10 to the 35th kilograms, and this turns out to be a mass of about 100,000 suns. So this is quite large.